Hi everyone. In this video we'll discuss a very important phenomena that can happen with stochastic gradient descent, which is basically gradient descent with over stochastic many batches, and that phenomena is Ill-conditioning of the Hessian. So last time we mentioned that for second order methods, right? So that's what we mentioned for second order methods. If you have a second order method, then the computation, the update of the parameter depends on H inverse G. So if H has a poor condition number, that could be problematic because you're very sensitive to errors in G. And condition number means that the difference, the ratio between the maximum and minimum eigenvalues is large. And that basically signifies what? So the eigenvalues of the Hessian represent the sensitivity of the cost function. The sensitivity meaning how much the gradient how much the first order derivative would change in the direction of the eigenvectors. So maybe, for example, if I plot a projection across one direction of the eigenvectors, the cost function looks like this, right? In another direction, the cost function looks like this. In the upper one here, the first derivative changes more quickly, right, than this one, right? So that means that the eigenvalue of the Hessian in the projection, in the upper projection, is larger than the one in the lower projection. High condition number means what? That there is a large discrepancy between the different directions corresponding to the eigenvectors of the Hessian, a large discrepancy in the second order derivative. So maybe one of them looks like this and another one that's very flat, right? So that why is that a bad thing? Because you're very sensitive to errors in G, because if the error happens in a direction that's very sensitive to the second order change, then going along that direction could be problematic, right? Why going along that direction could be problematic? Because let's say I have the steeper one here and I am at this point, right? The gradient would tell me to go to the right hand side, right? So it will tell me to go in that direction, right? Let's say I take a big step in that direction, right? So the gradient would tell me basically to go to, so this is one parameter, this is the x-axis. So let's say I go a lot in that direction, right? If I go a lot, maybe I go to this point here, right? Thinking that because of the gradient direction, I'm minimizing the cost, but I end up going to an area of a larger cost, right? That's even if it's not a second order method, right? So here I'm depending on the gradient to minimize the cost function, right? That comment was saying that for second order methods, the effect is even more explicit than this, because I don't depend on the gradient to update the parameters, I depend on H inverse G, right? So even the direction I use to minimize the cost function could be erroneous, right? Because that direction is very sensitive to errors in G, because there is a large discrepancy along the different dimensions or the different bases of that direction, right? So the bases correspond to the eigenvectors, right? And that direction has projections along the eigenvectors. If there is a large discrepancy of the sensitivity of that direction along the different bases, right, then a small error, if it happens in the wrong basis, could be problematic, right? So even for stochastic gradient descent, that phenomena that I just explained can happen, right? So even the gradient here can tell me to go in that direction. If I go by a large step, then I could end up increasing the cost, right? Why is this phenomena happening? Because if even the gradient descent, which relies only on the first order derivative, if we analyze if we do a Taylor series expansion of the cost, then a gradient descent step adds, it's true that if I take only the first order derivative component, it's a negative, right? So going in the negative gradient direction, subtracts from the cost minus epsilon times the norm of the gradient, which is G transpose G. If you think of G as a vector, G is the gradient. But it adds another term which typically we assume will be insignificant, but not necessarily, and in that case it will not. And that other term depends on the second order derivative, depends on the Hessian, right? That other term equal half epsilon square, where epsilon is the learning rate, G transpose HG. So that's why you need epsilon to be very small, right? Because let's say I divide these two terms to know which one will be bigger, right? So I take half epsilon square G transpose HG and then divide by the gradient norm times epsilon, right? So what you get is half epsilon G transpose HG over G transpose G. So that depends on the learning rate. So if I take a big step and G transpose HG is much bigger than G transpose G, right, then that could be problematic. So if I have this, then I really need to take a very small step, because if I end up increasing the cost, I don't want to increase it by much, right? Now that quantity here is called the Rayleigh quotient. And the Rayleigh quotient is typically a function of a matrix and a vector. The matrix here is the Hessian, and the vector is the gradient, right? And the range of that Rayleigh quotient for any matrix is called the spectrum of this matrix, right? Now that becomes important, analyzing that. So that's why if you read in any paper analyzing the Rayleigh quotient of the Hessian, of the second order derivative, or the spectrum of the second order of the Hessian matrix, can be important, because I want to understand how this quantity, which is the Rayleigh quotient, would be for different values of the gradient, right? So if the Rayleigh quotient becomes big, that's a bad thing, because that means that a parameter update corresponding to stochastic gradient descent would do the reverse of what I wanted to do. It would increase the cost function instead of decreasing the cost function, right? So to summarize, if that term G transpose HG reflecting the sensitivity of the first order derivative along the directions of the gradient, right? So which is basically the second order derivative information. If that term grows significantly with a small gradient norm, right? So the gradient norm doesn't shrink enough and that term grows significantly, then we would need very small learning rates and hence very slow training. Otherwise, you end up increasing the cost function significantly instead of the objective, which is to minimize the cost function by doing the stochastic gradient descent updates, right? So to recap, you can think of this term, the G transpose HG, as given the optimizer information about the curvature of the cost function or the change in the first order derivative, which I am relying on to update the parameters, right? So I'm standing at this point, what SGD would do, what stochastic gradient descent would do, is that it relies on the first order derivative, right, to update the parameters. So it's trying to minimize the cost through only information about the first order derivative. Now you can think of this term right here as incorporating information about the curvature so that you can know whether you should take a big step or no. If the curvature is, if the function is very steep, right, if the curvature is large, right, it looks like this rather than a flat like this, right, then I have to take very small steps, right? So if the Hessian gives me a large value for G transpose HG, right, so the second order derivative is very large along the directions of the gradient, these directions that I am using in my trajectory to navigate the cost function, then I should take very small learning rates or very small steps, so that results in very slow training. So the more the Hessian is ill-conditioned, right, the slower would be my training if I want it to be stable. The more the Hessian is well-conditioned, or it exhibits similar eigenvalues along the different directions, then I could trust it to have larger, I could trust the gradient direction to take larger and larger steps. Thank you.